Hey, hi everyone. Today is August 25th, and we have a working group Node Lifecycle meeting. And today's agenda is we will discuss NVIDIA's experience with Node Lifecycle by Ryan. First, I would like to ask if there is anybody who would like to introduce or has any news. Okay, just a couple of points from me. The meeting next week will be canceled because of the holidays in the US. And then in like half of September, I think September 15th, we will have a presentation about cured. So yeah, we are looking forward to that. And in the meanwhile, we are still discussing the caps a bit, but yeah, it's moving slowly. So Ryan, do you want to take it over?
Yep, I'll take it away from you.
Okay, please do.
All right. Okay. You should I'm just gonna minimize some things here. All right, can you just confirm you can see my slide here?
Yep, it's looking good.
Okay, great. All right, good morning, everybody. So I'm going to be speaking about NVIDIA's perspective of node lifecycle, and the goal is to provide everybody with additional information, additional context about use cases we're trying to address and are talking about in this working group. So NVIDIA's journey with node lifecycle has been several years in the making. To give you a sense of that journey, we started at a point, we were running a bunch of Kubernetes clusters and we were not doing any maintenance on these things. And now we're at a point where we're actually performing between 200 to 1,000 maintenance operations on any given day across our entire fleet of Kubernetes clusters. So it's a really big jump for us and a really important topic for us, and really giving us an ability to maintain our data centers and reduce our total cost of operations when running these data centers. So I'll do an overview of the solution we use, and feel free to ask any questions as I go through any of these topics. I'll be happy to expand on any of them as needed, and we can have discussions. So our infrastructure at NVIDIA spans more than 40 Kubernetes clusters. It's actually much more than this now. I just don't know the exact numbers. It could be even as high as 60, but I'm just using the numbers I've used in the past. So so I'll just say 40 plus, supports over 30,000 nodes and 60,000 GPUs. If you do a little bit of math there, that would mean 2 GPUs per node. And the majority of the workloads that we have running in these clusters are actually KubeVirt-based virtual machines, uh, running across both our compute and our control plane environments. We do run a ton of pods. It doesn't mean we're only running virtual machines. What I mean is that the tenant that we're supporting, a majority of the workloads are actually in these KubeVirt virtual machines. So we do have pods supporting those workloads, and so that's mostly like a lot of those pods that we're running are supporting these workloads. And so when my team first started working on these clusters, what became immediately clear to us and at the beginning of our journey is that we needed to carry out maintenance operations without disrupting users. It was very clear that we needed to incorporate this into our day-to-day maintaining of this infrastructure. And so our requirements when we first started thinking about this or doing maintenance is two things. First is that maintenance must not impact tenant workloads. Right, it's so critical. Pretty much anyone maintaining production infrastructure is going to have this requirement. And the second is that infrastructure must be able to take away, the infrastructure team must be able to take away capacity um, from the tenants. So this assumption, or this assumes that we don't have elastic capacity or hardware, right? Where that so it's an important thing to take into account with that second requirement. So those are the two things we're looking at when we're trying to figure out um, a solution. And I really like to use this analogy. I think this picture is great. I like to think about this as road work. I think this is like a bridge. Like I think when we're talking about infrastructure, a lot of what we're doing is we're providing a service for people who are using this. And I think a bridge is a great analogy. Is we have this bridge and we built it, and our tenants are like the people driving the cars over this bridge. And so when you think about our requirements, we really don't want to impact our workloads, right? We don't want to make it so that like we're pulling the entire bridge that these people rely on and away from them. And then, what are they going to do? They're going to have to go a different route, right? They would much like to drive over our bridge. It's not really useful to have a bridge that you can't drive on. And we also have this part about the infrastructure needs to take away capacity, right? It's almost like a dichotomy. Like how do we take away capacity, but we don't force people to not use our bridge, right? So we want this infrastructure to still be functional, but we still need to have a way to take away some sort of capacity from it so that we can improve it, we can fix it, right? We see this a lot in our world where we do, people, you'll see bridge lanes closed, right? Like it's the same exact problem space. And what's cool to think about is with this analogy is like Kubernetes actually has a solution for this, right? You could start a drain and wait, right? This works, and like the analogy would be like you pictured here, like you could throw up some cones on a road, right? You can drain this highway or this lane, so to speak, and wait, and eventually, like there'll be no people using that lane, and um you could do your maintenance on it. And so this is cool. This does work. But this approach has its limits, and at the scale and complexity that we operate, um, we wanted to see how we can improve this. And this is why it's been such a priority for us, is that this is really a process that has a lot of potential for improvement. So we want to reduce the total cost of operations. We want to have a way to meet our requirements. So what did we do? We, of course, right, we built an API, and Kubernetes is great because it provides a framework to be really extensible and create APIs. And we use this to as our direction. We wanted to create a maintenance API. So this essentially means that we wanted to have something that we could coordinate maintenance, and so we defined a bunch of maintenance states um, so we defined this object called the maintenance, and then we would define a bunch of states that every maintenance must go through. And hopefully this is familiar. These states here. So I'll read them 1 through 8. So schedule a drain, right? We go and if we want to do maintenance, we'll schedule a drain. We'll start a drain. We'll complete a drain. We'll start some maintenance. We'll complete a maintenance or we'll fail it. We'll start some validation, and then we'll complete it or we'll fail it, and then we can return that thing we're working on into production, right? So these kinds of steps are something that we should really see every maintenance go through. They should be really common amongst all maintenance. So we could define this through a CRD. And so that's what we did. Here's how it looks in the state diagram format. You might not be able to see all the letters there. These are kind of like the technical state definitions that we used. I have a link to this diagram if you really want to look at it more closely. We can look at it later, but um, I don't want to focus too much on it other than that when we define states, this is how they come out, right? We have a start, we have a middle, and we have an end to the story. And you can clearly define arrows for these things and clearly define steps for these things. And it provides this structure so that we can um, do things based on, what's happening in the structure. So that's really good. So this is what we call a finite state diagram, and this is what we call an API. So this is well, the name of this is, we call it a notified maintenance API. And the benefits for us is that we wanted to coordinate maintenance between operators. So these being the controllers that are running in our clusters, as well as humans too. So we want our controllers that are really doing most of the work, but we also want people to stay in the loop. And these different state transitions are our events, right? We can accurately describe what's happening, and we can move between these different states. And this creates a great picture for us to integrate a bunch of software into it. So this is cool. Now we get to a point that we implement this stuff, and we start seeing some results on this. And what did we see? We saw what we hoped for, which is that we saw some improved coordination. And first thing we did is that we would see that tenants, when they would see events for us doing a drain, they would preemptively drain things, right? They started to see, okay, well, hey, like the infrastructure team is planning to do maintenance here. Why don't we try and schedule out somewhere else? Or why don't we start trying to remove things? And then we also were able to agree with our tenant to some sort of SLA, right? So we kind of established this relationship where we said, like I said, is one of our requirements, like we need to be able to take capacity away. So these two things with an SLA, and we're seeing some improved coordination. This led to admins can drain to remove capacity. The infrastructure can drain, and then we saw no user impact. So this met our requirements. And what's great is we also saw some really nice improvements when we started rolling this idea out. We saw improved drain times, right? I talked about how tenants would preemptively do drains. They would understand that we're telling them about drains, so they would preemptively remove things. And so important, we would see deterministic drains. A really interesting idea that really led to a lot more ideas, because now we know that after a certain amount of time, something would be drained. Well, there's some things we can do off the back of that idea. So that's the next question. Can we do better? And so obviously the answer is yes. So we have an API that we're coordinating through, and we want to build more automation. So we noticed that a bunch of patterns now. When we rolled this out, we noticed that some nodes drain faster than others. And what's cool about this, I'll go back to my analogy again, like when we said from the start that, okay, you could technically do a maintenance solution today in Kubernetes. You could do a lane closure, right? Was the analogy. You could put up cones, close a lane down. But is that the most efficient way to do a maintenance? And the answer is no. Like there's better ways to do it, right? We see this all the time on our roads. Like we see traffic, right? We would never want to do set up cones on a 3-lane highway the during certain times, right? It's not an ideal situation. Or maybe some highways, so it's not, like maybe we need, different parameters to before we do it, right? So there's all these things that we can look at here to say, well, we can probably do this smarter. And so we actually found a few of these things. So we saw um, what were the nodes that had faster drains. So they had these characteristics. They had what we called pre-warm workloads. These were like our tenant would go in, cache VMs. They create them ahead of time so that when there was this sudden or surge of demand, they would have some sort of capacity already ready to meet it. So these kinds of workloads weren't actually serving a user, they were just sitting there. So they it would actually be faster if we were to drain those the nodes would drain faster if we targeted workloads, or we targeted nodes with those workloads, because there's no tenant impacts if we were to drain them, and they would drain immediately, right? They're really easy to get rid of. And then the obvious ones, which is like nodes that have very few workloads, right? So if there's one workload on a node, it's probably likely that that node's going to drain quickly. And then there's more like workloads that have been running for a long period of time. And this is another parameter of our infrastructure where our tenant has workloads that last a certain amount of time, and you could call them ephemeral. They won't last forever. There's sort of like an upper bound, like an artificial upper bound to them. So the longer they're running, the more likely they're going to be removed. So these three characteristics led us to see, okay, we can actually target nodes and we'll see much more improved drains. So this is cool. So we had this API, it helped us learn a few things and coordinate with our tenants, and we could take it even a step further. So I said, some drains are faster than others. So what we could do is we could actually start scheduling maintenance, right? We can chart a path through the zone, looking at nodes and saying, hey, this node is a good target for drain. This node's a bad target for drain, and so on and so forth, and kind of chart a path and schedule maintenances on nodes so that we can actually be really, really efficient with our drains. And so basically what this picture is showing is that we had that API that we developed, we had these states, and we were able to do drains. And then on top of that, we were able to build this controller I highlight here called like the maintenance scheduler. And that's what's charting our path through the zone and saying, okay, this is or do the Kubernetes cluster and saying, these are the best nodes that you should target and drain. And so that was really cool. So it's led us to a lot of really cool improvements that we'd see really fast drain times are much faster than what we were seeing if we were to just sort of cordon and wait. So this is all really good stuff that we'd see. But it continues that there's more automation we can do, right? Um, we noticed that some zones drain fast enough, some data centers. So we're regional. We have a lot of data centers in different cities, and we saw that there are um, other characteristics, right? Like that we see when you look at the zone level, right? You could look at the location, like somewhere in New York City or London and San Francisco, and they will have different patterns. Like you'll see there'll be periods where there's off-peak times, right? There's an ideal time to do a drain in London right now, and it's not an ideal time to do a drain over in New York because usage patterns are going to vary based on time zones, right? So we'd see all these things. So now what we could do is we would say, oh, well, we can actually expand this further. Like we could look at draining as not just a zone operation or inside a Kubernetes cluster operation. We can actually look at it as a fleet operation, and we can come out and design additional scheduler that says, hey, you should pick this data center, you should start drain, schedule drain and maintenance in this data center at this time, and so on and so forth. So you can kind of see like hopefully a picture in your mind how this sort of builds on itself, and gets to a complex system that is able to do all these maintenances at a global scale for us. So that's really cool. But what else though? There's sort of there's this is only half the picture. um, so before I go on to the next part though, are there any questions and before I'm gonna go to planned and unplanned maintenance? I can't see if there's any hands, so I don't know if there are any. Okay, I'll take that as there are no questions then. Okay, so planned and unplanned maintenance. So I said this is just half the picture, right? That what I was just talking about is this idea that we were able to figure out that this idea of drain could be efficient, this idea that we could do these drains efficiently and we can schedule in all different ways is all really neat and cool. But half of this is that half is sort of the planned maintenance world is what I'd call it. And planned maintenance is like planned software, firmware, hardware changes. And the expectation is that those changes are not going to break nodes. But we know in reality that that doesn't always happen, that sometimes things get unexpectedly broken. And it's not just during planned maintenance that things get broken. It's actually all of the time that things can get broken. You could have, I think, there's a lot of common ones. I mean, I'll go through the examples in just a second, but these kinds of failures occur and they occur randomly. That's the I think the central thesis about unplanned maintenance, and what ends up being a result is that the node is unexpectedly broken, right? So these are really important. We have to fix these, and we have to fix them all the time, day and night, so that our infrastructure is working. So we need to. So the important point is that we need to coordinate these two types of maintenances together. So we have that API. We're doing scheduling, so we need to coordinate them together, but we need to prioritize them differently because they are different. And um, so I'm going to talk about the prioritizing these things in just a second. So unplanned maintenance, pretty much like, well, what's the path for unplanned maintenance? Is that we need to do some sort of remediation. Perhaps we need to, escalate the remediation. We do reboots, we do IPMI power cycles on these nodes. Well, maybe the hardware is experiencing issues that we can't solve, right? So we need to triage these things. We can't just leave them sitting around and expect that the next planned maintenance that comes along is going to fix it. These things need to be handled a little bit differently. And so here's kind of how this looks. This is how we do it inside the clusters. Inside our clusters today, we'll use like the node problem detector. We'll use the node health check operator. So these kinds of things plug into this exact same diagram that I showed earlier, where we're going to have a bunch of states around maintenances and doing drains and scheduling maintenances, and there's going to be a reporting hierarchy from these two components. They would add labels to nodes, and then they would inform us that the infrastructure is not behaving as expected, and that we would use that as a way to flag this and tell us that we need to do something. And so what are these these maintenances, and like how do we prioritize them? So what's common is that we see these kinds of things as hardware failures. You see this actually quite a bit. You'll see this manifest in like the kernel message ring as the GPU falling off the bus. Pretty commonly, we will come across something like that. If you have enough GPUs, you will see it. We see software crashes, and sometimes this occurs because of an issue with hardware too. Um, and or even just on the on the driver's side, or even just even on the operating system side, we can come across all sorts of different things. And like I said, the more GPUs you have, you will see more and more of this occur. And for our perspective, we need to maintain this, and so we need to deal with these failures, and we need to incorporate remediations. And so these things need to be prioritized. So when we look at this in the scheduler's perspective, right, I said that unplanned maintenance is a broken node. Well, these things need to be prioritized immediately, and they need to be fixed. So planned maintenance and unplanned maintenance are coordinated together, but unplanned maintenance is a much higher priority. We need to get those nodes fixed as soon as possible. And then a good summary of like actually how this has been successful for us. So we'll prioritize these unplanned maintenances, and this is a picture about for us and we'll do 19 remediations per day per 1,000 nodes on average. And we used to get paged about these things. We used to get, as developers, the people maintaining this infrastructure, we used to get paged about this. We actually don't anymore. We had built this automation system where we're going to recover from these things with reboots and IPMI resets, and then eventually, we would send in teams to go look at the hardware. But this is how we would get through um, the day and dealing with these things. So we have quite a few of them, and this has been something that's been really important for us to actually um, maintain this infrastructure. Okay, so lastly, I before we go to any questions or discussion, um, the what I showed earlier, that diagram, and kind of what our work is. This has been open source. It's been published at this link. You can check it out yourself. Reason I'm mentioning is I think it's it's an interesting reference, and it's a good way to provide context for everyone to like to see what has worked well for us, and something that you can read on in your own time. It has a link. This link has that state diagram that I showed earlier. And then last slide, to conclude, NVIDIA's perspective. So these are the four things. Kind of if you were to summarize like all the things I talked about, this is what that would summarize them as, is that first, the drain API. So important to have deterministic drain. Actually, really, really important, and led to all of those things that I said, like where you can have scheduling and be really successful with draining, and being really organized with draining if you know when something is going to be drained. So that was something we found to be extremely powerful. And then there's lots of ordering too that has to go on, and priorities, like I talked about. You need to be respectful to the tenant, and so you need to do certain ordering, and that'll help you with building an SLA with the tenant. So I think that's really really important to have as a characteristic for the Drain API. Second, a native maintenance API. This one really important, and kind of what I showed is that for NVIDIA, our operations, we internally all use the API that I talked about for with the different states, and that works great because I mean, and those are NVIDIA's clusters, and we can have everybody integrate with those APIs. But the reality is that the when we introduce new software, we talked about, like I talked about, pulling in like node problem detector. Well, ultimately, what we had to do is we had to teach it about working with these APIs. And so it kind of highlighted the problem, is that really, like, there's a lot of entropy out there, that there's really no canonical API for doing maintenance, and doing maintenance on and lifecycle management. And having one would make it so that everybody, would be able to use that API, and so that you wouldn't have to do all these integration projects if you wanted to bring in new software to around and teach it to do lifecycle management. So having a single API that's native to Kubernetes would actually be really, really important. And the last two, node readiness API. I talked about one of the states being validation, and this has, I think, multiple facets to it, and that this idea of marking a node ready when it's ready for production work, right? It's not really a concept that exists today, but I think is really important, is that when you're doing maintenance and you're done with doing maintenance, right, you're going to need to make sure that the node is actually prepared to return to production. And it's really important to have a way to express that. And it's not just when you're doing maintenance, like you could even say today, like when you were running like just the device plugin in your cluster, and you have GPU workloads primarily. And if your device plugin is not ready, I mean, you can't really run any workloads on that node if all your workloads are going to require the device plugin. So, I mean, the question is, like, is the node really ready in that case to receive workloads? So there's sort of like some challenges there to think about. And then lastly, this one, so definitely something to think about. Something we have not solved internally, but definitely something that is on our minds, and it's maintenance in the world of multi-node workloads. Right nowadays, we're running workloads that are across multiple nodes because GPUs are being wired together, and they're running and they're being shared across multiple nodes, and it sort of creates this interesting matrix, not only from a scheduling perspective and like a day one perspective in Kubernetes, and I think there's challenges still there to be solved, but it also is extremely challenging on the maintenance side. And I don't know what the solution to that one is, but it's definitely something to think about, and I think will be really important for this working group as well. Okay, are there any questions or thoughts? I think I saw. Um, okay, it wasn't a question. All right, are there any questions and comments from people? That's all I have for slides. Is there anything people want to discuss specifically about the presentation?
Okay, I can start. Yeah, so I'm wondering like um how did you approach, like as you said, like the integration part with the applications is quite difficult like to do at like a large scale. So like you said, I'm wondering like what you said, like when you are also trying to detect the unplanned maintenances,
Mhm.
how does like the application actually handle these kind of maintenances or like I mean total disruptions?
Yeah, the way we were able to communicate this is that is actually exactly like I said, is that unplanned maintenance is our the node is broken. And so the way we explain it to the tenant is that it's like, hey, this node is not functional, and we need to fix it. And now there's some issue here. I'm kind of interrupting myself to say, like, there's nuance to this, which is that I said at the beginning there we have two GPUs on a node. So what happens if you had one GPU broken, right? Or one part of the node broken? Like I say, if we had 10 GPUs on a node and two of them were broken, right? So there's nuance here to say, okay, well, is the node actually broken? This is it's a really good question because it's very difficult, and the simplest way we were able to address this is by explaining to our tenant that, hey, this node is broken, and if we experience some sort of like a GPU issue, we need to take it down. So we keep it extremely black and white, black and white right now. We will say if there's a like, problem on the node, it's broken. We need to remove any workloads that are still there, and we go through this regular drain process. Um, but there are cases where it's completely broken and there are no workloads. So yeah, we basically it really depends on the setting, but it's all about that agreement that okay, this is a broken node and we need to take priority to drain it immediately or as soon as possible.
And do you actually like handle the speed of the drain somehow?
We will those ones we so no, we will go through like and those ones if we have like an unplanned maintenance and a tenant has a workload that's running there, um we will still abide by the SLA. We'll say, okay, like hey, like we're not going to give you any more like you're not going to get any more capacity on this node. So we'll actually take away the ability to schedule there and then we'll wait till the drain is complete. There's very few exceptions we would do it immediately, but for the most part, we'll abide by the SLA.
Even for the ephemeral workloads, as you mentioned before?
Yeah.
Okay, yeah, I think Ardestine has a hand up. Please go ahead.
Yes, I was just wondering if there is any fault tolerance mechanism or it is a simple drain that you use.
No, we just use a simple drain. So in terms of fault tolerance, we like if I think maybe the question is like about power disruption budgets or if we use them, then the answer would be no. So we just do a drain. We don't make any assumptions about the fault tolerance.
Because one of our use case for checkpoint restore is exactly, for example, if you have long-running applications like training, for example, model training, then you can essentially create a transparent checkpoint and then use that as a fault tolerance mechanism.
Yeah. No, that's an important use case. So on the only side that we would check for tolerance. I was thinking on the compute side there for a second. So on the compute side, like our tenant workloads, we will so with the ephemeral workloads, those ones we don't have any we won't use fault tolerance. The only ones we'll use is on the control plane side where we will create well before we start, we will check to make sure there's replication.
Thank you.
Yes, so if I can jump in between. So you basically try not to use the disruption budgets, but you have like a custom logic like built around your states and like what you want to achieve?
Yeah, we don't use the disruption budgets. Yeah, so we just use the states, and if we will, the only thing we'll do is that if we'll because we'll use like 3 replicas, so for example, or multiple replicas. So and we'll only do one at a time. So so it'll leave us even if we were to like do drains, we would check beforehand and say, okay, there's 2 other replicas, at least 2, so we can start a drain. So we'll just gate that way.
Okay, Jonathan?
I was on mute. First of all, Ryan, it's a good presentation. It's funny. I'm a maintainer on Carpenter and work at AWS, and I see a lot of the same like logic appear in that autoscaler because we do a lot of remediation logic on our side as well. Like we do drain orchestration through a controller. We do checkpoints based on whether things well, because we consider pod disruption budgets, so we obviously validate like whether the nodes are even disruptible in the first place. We have timing mechanisms where you could set disruption budgets. Like all these things are kind of on the nodes themselves, or these things are kind of there for the most part. I think right now, like the readiness API is kind of an interesting point. I'm assuming that is an issue because of like restart handling. Like in general, like we've seen users use that like taints and then remove taints to kind of signal the fact that things are ready when the node first starts up. But how do you handle that on like a restart? Because I assume that y'all are doing that when you do maintenance operations.
Yes, we do. Yeah, so that's a really important point. So yeah, when you restart, there's the question of like, did it really work? This is a huge problem for us on the unplanned maintenance side because what we'll end up doing is we will loop many times. Like if we have sort of say like a driver failure, we'll immediately reboot, and sometimes it doesn't work. And so we actually don't want that node to return to production. And we will validate it and say, okay, no, it didn't work. So we need to go something more, um, we need to go something else that didn't work. So we'll do like IP my reset. And then if that doesn't work, right, the node's still broken, so it shouldn't be marked as ready. We need to have people to come look at it. So we kind of call like an RMA process where we'll just say, okay, look, someone come look at this node.
Got it. Okay, I think that makes sense. And then one other question, because I did actually want to like expand on the multi-node workload scenario. I think we're also thinking about this problem as well. I'm curious if you had, I know you kind of touched on it briefly, but I'm curious if you had any additional like thinking from y'all side with your use cases on how you kind of are starting to think about that problem. Like there's kind of a tie between gang scheduling and gang maintenance in a way, right? Because if you have a workload that is trying to schedule together, it's most likely trying to disrupt together because it's a cross node workload of some kind. And I know there's some thinking about this in the community around like there's workload scheduling. There's a conversation starting to happen around that, and there's going to be a discussion at KubeCon NA about workload scheduling. And I'm curious how you think about like that in the context of disruption, and if you have any thoughts around how like Kubernetes in general should solve that problem.
So I think there's still early thoughts because I think from our side, like I think this is like sort of unexplored territory because where a lot of success we've seen so far, we like you kind of can see like we made certain assumptions to simplify our approach, and this like multi-node part is takes a lot of those simplifications away. And so like when I think about it, like I think about today, like the process that a workload goes through just to schedule on multiple nodes, and then and like the challenge, like there's like many challenges there, and like the one I like think about a lot is the case where say you had 3 nodes, three different GPUs and one workload, so 3 pods across each node. What would happen if only one of those pods went down, right? Like you just lost one of them, and it could be for any reason, right? Like could be like I talked about driver failure. Could be there's a driver failure on that node and the GPU is broken, and or even just the pod went down for any sort of reason, right? How do you fix this? Like how do you reschedule now a third pod? So like there's like so like the way I'm thinking about it is that there's sort of a coupling here between the Kubernetes scheduler and now what we're doing for maintenance. and this is where it gets really difficult for me um because now like that node needs to go through unplanned maintenance. It is broken. So kind of in the world that I've described today, we would find a way to mark it or communicate that it's broken in some way. And then the idea would be that the Kubernetes scheduler would understand like, hey, look, we can't use that node anymore for this workload. We'd probably have to checkpoint the workload or something and go through a rescheduling, either of the whole thing as a gang, or if there was a way to reschedule just one pod, we'd have to do it that way. But I don't know how possible that is. I really explored that, but that's kind of the way I'm thinking about it, is that there needs to be some communication to say like that node's broken. Like you can't this workload that you've gang scheduled is actually needs to be rescheduled.
Yeah, interesting. So when you say rescheduled, it's just the workloads on that node, right? Like the other workloads across the other two nodes should still be good. Or you're saying the entire thing needs to get rescheduled for that
So
scenario?
I'm not yeah, so I am this is where I don't know. Like so this is where I don't know because you correct like to say that you perhaps like it would be nice to say like you only need to reschedule the pods on that one node to a third node. But there's sort of the question here is like about the internal details of the application, because now how is the application going to function in this scenario? Like, is it going to function? Is it going to work if we just start up a new node with a new workload? Right? Like, there's sort of that's kind of what I'm wondering is I actually don't know the complexities of this to say like for sure if it's as simple as rescheduling one pod on you know in that case of three pods scheduling one of them, or if it's needs the whole thing needs to be rescheduled. So that's sort of like an open question to me. It's like I think there's a lot of complexity there. So the part that I'm only focusing on, at least at this point, is that I think there needs to be a signal to the scheduler. What the scheduler does, I'm not sure yet. It would be interesting to talk about that. I don't know the answer though.
Yeah, that's interesting because like you obviously with these GPU workloads, you have all this topology that kind of comes into play when it comes to the racks and their placement. And
Yeah,
you're right that
exactly.
if you have to schedule a new node and that node is just happens to be in a different placement, or you can't get placement that is like similar enough with your scheduling requirements to the nodes that are already there, then you probably would want to evict the entire everything and then reschedule to somewhere where you can schedule everything like with reasonable placement. But if you could get like good placement for just one node to add to that, those other two that already exist, then you probably would prefer that. But you can't know that until you try. So it's kind of, I get your point. Like it's a little bit challenging. I do. I wonder if any of us in the working group are. I'll have to post this after the fact. I'm on my phone right now, but I don't know if anyone's involved in that workload API discussion or workload scheduling discussion that's happening in SIG scheduling. It'd be interesting to kind of get additional input into that discussion. Um, because I think it does relate to the problems that we're trying to solve here as well when it comes to like that specific issue.
Yeah, yeah, I had a short discussion about this with them, and they are certainly like interested in the work we do, and there is certainly an overlap. And I think they are trying to design their APIs in a way that you could actually target a workload as a whole in like scheduling or rescheduling case, or like a resource reservation case. So, and I think what I saw now, like they are still like in the defining requirement stage. So we will certainly like have like a more like in interactions with them, and I think they even said they might do a presentation in this group to actually see where we stand.
Yeah, that would be cool.
I had one more question if you'll hear me. The last one was, how do you handle like cluster churn when it comes to scheduling operations? So if you're determining like, hey, this node needs to go into maintenance, and then this one should come next, and this one should come next, and then like the topology of your cluster just completely changes like within that time frame. Like, how does your controller react to those changes in your cluster topology, or is like the topology so predictable that it's like not that challenging and you're just able to like programmatically, deterministically like schedule out all the operations that need to happen in order.
It's mostly predictable. We learned over time that it was mostly predictable. I mean, I can tell you about the workload. It's most of it is actually for cloud gaming. So people are playing games at certain times of the day, and so if we have a sense of seasonality for our workloads, like people are playing like after work, like between 6 p.m. to midnight in their local time, or sometimes in the morning, and they're usually not playing from like 10 a.m. to 2 p.m. or something, just as an example. So like we have these seasonality pattern. So the topology doesn't really change a whole lot for us. That is sort of changing over time. Like as a caveat to this we've been is that obviously when we have off-peak times, we want to use those capacities. So we've started to introduce more things into our data centers to use those GPUs. We'll do some, I think we do some inferencing and stuff. Right now we use it as like spot capacity, but that may change. But essentially, right now is we have a very deterministic picture of it. But that so it's easy for us. So like I said, the assumptions right now it's a little bit easier for us to determine, but that will probably change over time.
Cool, thanks.
Okay, any more questions from people?
Do you have use cases for like a partial drain of the node?
Partial drain. Let me think. So, um, I don't think so. I think this is a good question. I think this is another one of those ones where we wanted to simplify. It was easier for us to approach this is that if we're going to drain, then we're gonna take the whole thing away. Um, it just simplified a lot of the equation. So I haven't thought about it a ton, but I don't believe we have a use case for it. At least I can't none come to mind.
Okay. And yeah, one point I noticed about the node readiness API. I think there is a feature like proposal in Signode about node readiness gates, which could be used for like this sort of signaling of different kinds of like readiness or like feature availability on the nodes.
Yeah. Yeah, no, that one's really cool. I think so. The important thing that in mentioning here, because I'm aware of that cap, is that I think a bunch of these things, actually all four of these things are sort of tied together, and that readiness in isolation, like I think the use cases are probably like maybe you want to define like I think the example I used was that if you're using primarily GPU workloads and if your device plug-in pod isn't ready, then is the node really ready, right? That's a very clear use case. But there's more like I talked about here with maintenance is that technically validation is actually like before something returns to production, you would want to do something to it. So node readiness sort of takes on a different use case there. And so that's where like when I kind of like to relate these together in that when thinking about a drain API, thinking about a native maintenance API and the node readiness and even the maintenance and part for multi-node workloads, that I think all these things kind of need to work together and be aware of each other because there's a bunch of use cases across all four of these, I think, to really get to, full maintenance picture. So my point is that I think like these caps, it'd be good to even bring some of that cap in here, and when eventually like we're talking about Drain API and probably soon the maintenance API, and like really trying to weave these together. There'll be I think there's gonna be a bunch of use cases when we overlap them.
Yeah, certainly. Like there is a big overlap, and like one like feature which is also important to this is the graceful node shutdown, like which the Signode is very interested in graduating. So I know like there are like a couple of cases in the graceful node shutdown where you can actually lose the drain signal or like the shutdown of the node. And there can be also like different cases what you want to do after you shut down, like if you want to restart the node or like what happens to the node after. And like most of this feature is like driven like by kubelet, and like there is actually no like extension through the API to actually see what kubelet is doing and how it is progressing through the shutdown. And yeah, and it's about the life cycle of the whole node. So like we like it's expected we would like to also look into this.
Yeah, that makes sense. Yeah, we go
Yeah,
through that a lot too with unplanned maintenance. I mean, all the time. Yeah, like you said, so I guess we don't call it graceful node shutdown, like, or we don't actually use the feature on our side, but we'll do a drain and then we will effectively do the same thing. Like we'll remove pods and then have the kubelet help us, and then but we will just track it differently and then like states.
yeah. So like I would like to mention like what is the follow-up to this. So we have like this enhancement issue opened for like declarative node maintenance, which I started writing a cap, and then Ryan also did his take on this in like a different branch. So yeah, I saw like that it like your work references like what you would like to see from NVIDIA's perspective, which you just shown. Like I think it's like interesting take, but we need to like find some compromise, like what we want to do for what works for you and also for the whole community. So I think we should like try to maybe review these like different like approaches to this cap. Maybe also on the call. What do you think?
Yeah, no, that would be good. I think we should talk about it sooner rather than later. I think it makes sense.
Okay, cool. So yeah, like we will try to schedule it like when we both have time. So let's see. And yeah, we will put it to the agenda. And I think we are closing to the top of the hour. So anybody has something last to say? Okay. Thanks everyone, and like see you in 2 weeks.
Awesome.
Bye.
Thanks, everybody. Bye bye.